All right, this is project 3, um, and for class C, CS 447. Gonna walk you through the breadboard. What we're doing here is we're trying to hook up the HC05 Bluetooth module to change the frequency output of a speaker, as well as the onboard LED of the TM4C. I have a 8-bit DAC out going through R2R into the speaker with filtering capacitors and a amplifier to boost the signal so that the sound comes out a little bit better. Two breadboards hooked together, one board for just the Bluetooth and the other for the DAC and the speaker, and that's about it. In the code, we can go through pin connections and kind of talk about which wires are connected to what. So let's go ahead and turn. Well, we'll just leave that off for now, and then we'll go through the code, and then we'll turn it on and show you kind of what's going on. So sound file, same as it was from previous labs. Same sound output with the sine wave. DACnet is port B. We have a double F here going for pins 7 through 0. Sound init now takes in a select as well as the period for the Cystic counter, so reload count value. And then we're going to determine a high and low here for the duty cycle for the LED. DAC out's pretty straightforward. It just takes the data in and outputs the data through the different wires to my R2R. And then the main meat of it here, the Cystic handler, has two cases. If you put in an F and then some numbers, it's going to output to the speaker. Otherwise, B and some numbers is going to set the duty cycle low and high based on whether the LED is on for PF2, which is the blue LED. And then we got some debugging code down here, but that's about it. And then otherwise, it's just going to break out and do nothing. So if you don't give it the proper commands, it doesn't do anything. So we're accounting for some, unknown changes or data that we don't want. All right, so this is the main program here. Let's see. We're setting up port F for the LED. Some includes headers for different functions used. Different data structures here to store variables to store the information can be used. Port F for initializing the LED, a delay for wait, enable and disable interrupts for setting up the information and then turning them on. Cystic handler, convert functions for both the frequency and the brightness of the LED, so that way we can get the input to convert to a range we want, a range of values. Parse digits left over, didn't actually end up using it. So you can ignore that portion. And then here in the main code, we have disable interrupts, and then we enable all of our port Fs, PLL, and loop for the 80 megahertz clock, the DAC output for the board, and then we have UARTs 0, 2, 3, and 4. 0 was using for debugging, so I was printing on the through PuTTY, through the terminal console. And then 2, 3, and 4 are used for project specification to simulate having two boards, but I only used one, so we use multiple UARTs to simulate UARTs on other boards. And then we had some test code here, which we're gonna comment that out. First thing in the while loop, main while loop here is it grabs the first char, which is either going to be an F or a B. If it's not, then later on we'll show you nothing happens. So it's only those two cases that we really care about. And then for debugging purposes here, we have another output to the UART console, but that's not necessary. And then in turn, we're going to take the next few bits of information that are taken from the UART. UART2 is connected to the Bluetooth. So as the Bluetooth sends and receives messages from the phone, we're going to get that information. And then we have UART char buffer taking in and outputting. Let's go ahead and comment this one out too. That's just outputting information to the console again, but the main part is that we're taking the information from the Bluetooth UART and storing those chars in a buffer array. And then here we are going to output. This is the part that simulates the transfer from one microcontroller to another. We're just sending the data from the UART to the other UART, sending out char and then an in char, and we're going to collect that data back into the same buffer. But the important part here is that the data sent out is replacing the data that we previously had. So if it goes out and doesn't come back right, then we have a problem. If it goes out and comes back right, then we know that the simulation of two microcontrollers is intact. Some debugging code. The main switch input here just cares about a case F again and a case B, otherwise you do nothing. So that's how we account for information that's not what we want. And then both cases are fairly similar. Case F turns off the LEDs, so that way when we're looking at the sound, we don't care about the LEDs, so we'll turn them off. And the same is true for the reverse. When we're doing LED, we send zeros to the data for the speaker, so that way we can get rid of that as well. And then period gets the array to integer of the buffer, so we're converting the buffer into the period value. Then we're going to disable interrupts, enable the sound init, converting using the proper function the range of the period into the correct numbers to use for the sound init for the sysdig count. And then the same is true for down here. Turn off the speaker, convert to intensity, and then we use that intensity to convert the blue LED. And then we use the B and the F to give the sysdig that F or B that we're going to use to get our stuff. Port F and init, pretty standard here, same as previous labs. Just turn it on 1, 2, and 3 for LEDs. Although we're only utilizing PF2, which is you could use a 4 here. But anyway, I just made this one low just to be sure when I initialize it. Delay. And then here's the two convert functions. So I got these from an online calculator that you input a range of values, and then you input a range of input that gives you values only inside that range. And so it gave me these functions. This is the function for the frequency, so any number between 262 and 494 will give you the range for the sysdig count to produce those proper sounds, and same is true for the LED. This gives you a duty cycle, and then in the sysdig handler and the sysdig sound init, that's what determines the duty cycles on and off. And then we have some debugging code down here, useful for going back and looking at your code, checking data. UARTs, using UART2, UART3, 4, and 0 was used for debugging. UART in chars, non-blocking, could have used it, but avoided it. Out char for all the different respective UARTs. tm4c.h header file, startup file, and that's all the code. All right, so now we're going to compile the code, and we're going to download to the board, and we're going to reset, and then we're going